Assalamu alaikum. Welcome to another episode of Operating Systems. My name is Dr. Bilal Wajid. Now, in the previous two episodes ago, we introduced the principle of scheduling and we discussed two fundamental elements. One was what is called the turnaround time, which is the difference between when the job starts as opposed to when the job ends. And then another metric called the response time. I mean, how much time does it take between the first instance the CPU runs the process as opposed to when it actually came? So these were two fundamental metrics. And we discussed some basic scheduling paradigms starting from the first in, first out to the shortest job first, and then to the shortest time to complete first, and then the response time, and what happens when there's input output that needs to be done. Now, in the latter chapter, we discussed multi-layer feedback queues and how can you update the mechanism of multi-layer feedback queues to accommodate or to avoid starvation and to avoid being gamed, gaming tolerance. Now, this particular lecture is more about developing a scheduler that's not really optimized for turnaround or response time, but rather guarantees that each job does get a certain percentage of CPU time. So here, the primary focus is on fairness. And we will introduce a metric of fairness. But the primary focus is that, I want to ensure that my job or whatever jobs are there in the CPU are guaranteed certain percentage of the CPU time that it runs. Now, it's usually done by two frameworks. One is called lottery, that's one framework, and the other is called stride. And we'll discuss both of them. So here, let's consider the element of tickets. So let's say process A has 75 tickets and process B has 25 tickets. So the global count is 75 plus 25, that's 100 tickets. So even 100 tickets, process A should receive 75% of the CPU time and process B should get 25% of the CPU time because the total global count of both tickets, process A plus B, is equal to 100 tickets. So the percentage of tickets relative to the global count tells you what percentage are they going to get the CPU's time and attention. Now, here is an example. Here there were 100 tickets. This was the global total. A having 75 tickets ranging from 0 to 74, and B had 25 tickets ranging from 75 to 99. So from 0 to 99, you get 100 tickets. And what you see here is interesting. What you see here is that at every instance, whenever there needs to start, in every time slice, a random number is generated from 0 to 99. If the number is ranged between 0 and 74, inclusive of both 0 and 74, you can say ARAN. But if the number is between 75 and 95, inclusive of both 75 and 95, you're going to well say, you know what, B will run. So over here you can say because it was 63, you ran A. Because it was 85, it's between these two numbers, you're going to run B. Again, in the next time slice, a random number is generated. The random number happens to be 70 because 70 is between 0 and 74. A is going to run, and this is how it goes. So the lottery scheduling has fundamentally two elements in there. The first is the tickets, and the second is the random generator. Now, the scheduling framework is has several advantages going for it. But what is essential for us to understand is, because it's a random number, probabilistically over a large amount of time, A will get 75% of the time and B will get 25% of the time, but over a larger duration, not over small durations. So, for instance, in this particular instance, you could see there are 20 instances of A and B, and 25% of 20 is 5, but B occurs only 1, 2, 3, 4 times. So B is not getting the 25% that you would expect. It's actually getting 20% of the CPU time share, for the first 20 slices. And that's completely understandable, because think about it. If you roll a dice, if let's say A and B are equally, they have the same number of tickets. A has ticket 1, 2, 3, and B has ticket 4, 5, 6, and you roll a dice. You could get one, then A gets to work, and then the next time you roll a die, you could get two, and then A could work, and the next time you roll the die again, you could get two, and then A could run again. Right? Because you can see here, you have 63 here, and again you have 63 here. So the random number is generated between 0 to 99. So in the first three instances, all three times it was A that got to use the CPU time rather than B. So, I mean, probabilistically, these frameworks work better if the jobs run for longer duration. But for shorter duration, this is not entirely a fair mechanism, because it's not really giving it the percentage that you were expecting. So there is also this element of ticket currency. So ticket currency is that, let's say a system converts the currency into the global value. So let's say A and B are equally important. Okay, they both have 100 tickets each. So they're equally important. You could say they have share the same priority level, as opposed to the previous example where A was at a much higher priority level as opposed to B, extending the concept of MLFQ here. So over here, A and B have the same priority level. Both of them have 100 tickets allocated to them. But, you could do something different here. You could, what is otherwise, you could allocate more tickets to upgrade your framework. So let's look at this, for instance. You had 100 tickets, and process A, user A itself, uh, and think about this. Let's say there's a user A and there's a user B, and they're both trying to access the server, and they both have equal priority. It means this, as far as the server is concerned, both user A and user B are equally important clients. Now, what user B does, and it gives user A 100 tickets, and it thinks, user B has 100 tickets. But what user B does, it says it sends out 10 tickets. Okay. Whereas what user A does, user A thinks, I'm more important. My jobs are very important. So I have two tasks for the server. One is called A1 and the other is called A2. And I'm going to send 500 tickets each to A1 and A2. Whereas B is only sending one task to the server and it's allocating only 10 tickets. Because user A and user B are not talking to each other, they both want to access the server. They both want, user A feels that the job that he's doing is much more important and it should get done quicker. What the server can do, it can accommodate or produce a correct global value, one that introduces the element of fairness within tasks or of the same priority. So here, user B, although it sends 10 tickets, it would count that as 100. Whereas these 500 tickets, they would be counted 50 each. So in total, you have 200 tickets, which is the global currency. And each of them, user A is allocated 100 and user B is allocated 100. This ensures a level of fairness. Now, you could also transfer your ticket to another process. So, for instance, a process can temporarily hand over some of its tickets to the OS because it requires the OS to do a certain number of things. Like, for instance, in the earlier discussions, we talked about fork, we talked about wait, we talked about execute, and this is the process, these are process system calls where the user itself hands over the execution to the operating system saying, hey, listen, why don't you do this for me? Okay, so in this particular instance, the process can actually transfer or hand over some of its tickets to the OS so that it does get the allocated share of the CPU that it wants. There is also ticket inflation. A process can temporarily raise the number of tickets it owns only because it wants to tell the OS, listen, I am doing something which requires, an extensive, it requires, these are important calculations. I want the CPU full time. Please, I'm going to increase the number of my tickets. So this is also something we can do. So if a process needs more CPU time, just boost the number of its tickets. Okay, so here is a simple example, okay, of three jobs A, B, and C. And a simple implementation, you see a linked list here, and job A has 100 tickets, job B has 50 tickets, and job C has 250 tickets in this particular instance. So, I mean, the total number you can see is 100 plus a 50 plus 250, that's 400. So, the random generator actually uh, generates any value between 0 and 399, or between 0 and 400, because the total number of tickets are 100 plus 50 plus 250 in this case. And let's say, randomly you say the ticket value is 53. No problem. You're going to start with head. Because the ticket value is 100 and it's 53, A is the winner. A is going to do the job. But now let's see, you run the random generator. In the first time slice, A ran. But in the next time slice, let's say the value comes out to be 350. No problem. You're again going to start from the head. The first job is 100. Well, it's less than 350. No problem. You move ahead, you know, then you come to 50. It's 100 plus 50. That's 150. 150 is still less. Then, what do you call the winner, which was 350, and then you go to the next job, which is 250. So now it's 400. Definitely 400 is more than 350, so you stop there and you've got your winner. Now in the next time slice, I'm going to run task C, and that's what you see here. You're going to continue updating current to the number of tickets it has up until you go above the winner, and that is the point. That is the node at which you stop is the task that you run. And hence now, and so the lottery mechanism is very easy to implement. All you need is simply a random generator, a data structure like a linked list, and a few variables, and you're good to go. I mean, it's actually that simple. It's very simple to implement. And moreover, you can add newer jobs. You can just add another job like job D, and the job D is added at the end, which is the tail of the linked list. And, job D can have 50 tickets, and that's absolutely fine. Really, that's really absolutely fine. It's fairly easy to add newer jobs. And it's also easy that if a job actually finishes its task, to remove it. It's a linked list. You know how to operate linked lists. The pointer that goes from A to B now just simply goes from A to C, so that the current dot next is in fact A C. It's not B because B has already done the job. So the idea is that lottery scheduling is super easy to implement. It is very fair over long durations. Um, it only requires a linked list, and people in generally know about random generators. They know about linked lists, and so this is a scheduling framework that they can apply fairly easily. Now let's go back to this idea called fairness and an unfairness. Here, fairness would be, let's suppose there are two jobs and each job has a runtime 10. So fairness would be if job A finishes at nearly the same time as job B. So both of them, they started at the same time, they should end pretty much at the same time. If they do, fairness is one. But if job A finishes in 10 times, put stamps here, and job B finishes in 20, it's zero point 0.5. It means it's pretty unfair. Job A got to finish first before job B. Even the response time is bad in this particular instance. Okay. So, as I discussed, because lottery is based upon randomness, we know randomness behaves better as expected over longer job durations. And we see as the job length actually increases, the fairness criteria or the unfairness criteria, scoops closer and closer to one, indicating that in fact the number of percentages that you expected, the percentage time of the CPU that you expected, is in fact this percentage of CPU time that you are receiving because you have the right number of tickets. Now, another framework is called stride scheduling. Now, stride scheduling is interesting because um, I mean it's also very fairly easy to implement. I mean to understand. So, how does stride scheduling work? The best example is the one that you see in this. Okay, you have stride A, B, and C. All of them are arriving almost at the same amount of time. When they arrive, here the principle of ticket is replaced with the stride. So if process A has 100 tickets, the stride of A is 100. If the total number of tickets is, let's say, a large number like 10,000, you're going to choose a large number like 10,000 and you're going to divide it by the number of tickets in the process. And that gives you the stride of that process. So if the large number is 10,000 and A has 100 tickets, well, what is 10,000 divided by 100? It's 100. So the stride of A is 100. But if process B has 50 tickets, then 10,000 divided by 50, well, that's 200. So the stride of B is 200. And the idea is, you know, I'm going to run a process and increment the counter for it by its stride. And when I do for a particular process, I'm going to pick the process at every given time slice. I pick the process which has the lowest pass value. What does that mean? Let's look over here. Here you have A with a stride of 100, B with a stride of 200, and C with a stride of 40. So I think C has 250 tickets because 250 10,000 divided by 250 is 40. So that's why the stride is 40. So initially, because all of them have the value 0, A runs. Once A has run, you increment its counter to 100. Now, in the next time slice, you're comparing between 100, a 0, and 0. So you can run, you run at every time slice, you run this task with the smallest pass value. Here, B hasn't passed at all. It hasn't even run the CPU once. So in this particular instance, you run B. Now, once you run B is updated by its stride value. So B's stride value becomes 200. In the next time slice, you're comparing between 100, 200, and 0. Well, because 0 is the smallest, you run C. In the next time, and then you update it with its stride value, so C becomes 40. In the next instance, again, you're comparing 100, 240. Again, you run C. Again, you update it to its stride, which becomes 80. Again, in the next time slice, you compare between 100, 280, because 80 is the smallest. Again, run C. Now that it's updated to 120, in the next time slice, you see you compare between 100, 200, and 120, because 100 is the smallest. Well, A runs, and A is now updated to 200. And so this is how it actually works. Now, the problem with stride, the good thing about stride scheduling, it's again, it's very fair. It has a better fairness value, but it's not really. I mean, you had lottery scheduling, which worked well if the jobs were longer. Here it works well even if the jobs are shorter. So it does give this fair amount of time of the CPU as is expected by the number of tickets or the stride value of that particular process. So it's good even for smaller tasks. What's the problem? The problem is if a new process comes, it doesn't handle new processes very nicely, because if a new process comes and you were running A, B, and C, well, think about it. If a new process comes, like A is already at 200, B is already at 200, and C is already at 200, and the new process obviously will have a pass 0. Why? Because you didn't run it even once. So, and if let's say its stride is 10, it comes with a lot of tickets, and it's tried it's 10. So the number of tickets, 10,000, the number of tickets is 1,000. It got 1,000 tickets. Now, every time D is going to run, because the pass value was 0, it'll update to 10. In the next time slice, again, D will run because the pass value is 10, it'll be updated to 20. D will run 10 times before, 20 times actually, before the pass value reaches 200. So now A, B, and C are being starved off of CPU time because, D just came in new. So this is a problem with this process. It doesn't do well, or a new process really monopolizes the CPU. Okay, so thank you very much. This was a shorter lecture in the sense that we only discussed 2 components. Inshallah, in the next lecture, we're going to do more. Up until next time, thank you very much. Allah Hafiz. Bye-bye.